So the last thing we'll do is the BlueSaw cuts to find the internal force equations. There are some formulas that we are going to need the equation of the internal force. Definitely the beam equation, we're going to need m of x. So what we're going to learn is a skill of how do we cut this thing at a distance x. And so it's actually quite easy. We're going to just take our BlueSaw out and we are going to cut this thing twice. We're going to cut it on both sides of the vertical load. So I need to cut it somewhere between A and B, and I also need to cut it between B and C. So we're going to do this thing one piece at a time. So if I just take that BlueSaw out right there and I cut it, right, that is the at BlueSaw at X on Twitter, a shameless plug right there. And so we end up with now two free body diagrams, one on the left side, one on the right side. Please note the dimensions that show up here. I've cut this thing at a distance x. Between A and B it was a distance of 15 feet, so what's left over on the other side is 15 minus x. Still sitting out there is segment BC. Now both diagrams have to give us the exact same answer for the internal forces. So I can use either side to go do statics on. Looks a little bit easier if I'm going to use this side to do the statics. For one, I kind of avoid that 15 minus x right there. So I'm just going to do three equations of equilibrium. I'm going to spin a moment right at the cut to go ahead and solve for m of x. I'm going to sum forces in the x direction to find p of x, and sum forces in the y direction to find v of x. So if you want to go ahead and do that, pause the video. Here's your answer. Summing moments at the cut. I find that, again, m of x is a function of x. The internal moment is not constant from A to B. The internal axial force, p of x, is a constant, equal to minus 4.47. And sign convention, when I don't know an internal force in the axial direction, I'm going to draw it in tension. Therefore, negative will always be compression. Also do statics in the y direction. Sum some forces and I find Vx. So there's my equations right there, there, and there. Got to cut this thing again. I need the internal forces now in segment BC. So I need to cut that thing at a distance x again, but that now the distance x is going to be between B and C. And what I'm going to do is highlight the right side of the free body diagram. It's going to be less forces on it, so it's sitting right there. If I cut this right at a distance x, that means that left over would be 15 and 5 is 20. That's going to give me 20 minus x left over. So as long as I can dimension that side, I can go ahead and use that side. So very quickly I can again spin a moment, sum forces in two directions, and I'll have all the internal force equations. And there's my answer for my internal forces. I end up with 0 in the axial direction. I've got a different moment equation. And again, I have a jump. My shear has also changed. Still a constant, but it's changed. So again, summarizing our diagrams, and this is just what we found. Again, both ways, both using the load shear moment relationship and also the BlueSaw at a distance x. And so we would end up just plotting these equations, and we end up with the exact same diagrams. Right, the shear jumps, right? It remains a constant. Same with P. It jumps and remains a constant. M is a first order. And if we went ahead and plotted the equations that we just found, again using X to find on the left end of the beam. So this would be X equals 15. This would be X equals 20.